Till now we have always been talking about free oscillations of a system. Today we'll start looking at forced oscillations. Okay, and I'm going to be interested in one-dimensional system. One-dimensional system. Okay, we'll talk about a system with more than one dimension later. Okay, that's one thing, and then I will be interested in looking at this one-dimensional system, and we'll assume that there is a force which is acting on this system externally, and that external force is a sinusoidal force. Okay, because that is what most generally you will be interested in, because if you have your system on which a periodic force is acting, then you can decompose it into sinusoidal forces, sinusoidal components, and that's why we are interested in looking at forces which are sinusoidal. So let's look at the equation of motion for such a system. So I'll have the Euler-Lagrange equation will be d over dt del L over del q dot minus del L over del q equals, here you will have your generalized forces. Remember our first few lectures where we talked about generalized forces. So that I put in here, and the Lagrangian of my system will be described by half q dot square minus half omega square q square. Okay, so which means that the omega is the natural frequency of the system, and I have chosen the coordinates such that the coefficient here is just half. Everything else has been absorbed into q. Let me write down here F, or not there, maybe F is the generalized force. Okay, now if F is equal to 0, it vanishes, then you have a free system. Okay, and the solution to the free case you already know, is this. Q is A, let me see whether I'm using A, yes, A cos omega t plus alpha. Okay, and your equation of motion in this case is Q double dot plus omega square q is equal to 0. And remember, this is a homogeneous equation. Okay. Now I want to assume sinusoidal force, as I said. So I will take the generalized force F to be some constant f, small f, and then you have cos gamma t plus beta. So the frequency I take to be gamma, okay, of this external agency. And now our equation of motion is q double dot plus omega square q equal to f cos gamma t plus beta. Okay, note I have taken different alpha and beta here. So I mean, you can choose one of them to be 0. So let's say you can choose alpha to be 0, which is basically equivalent to choosing what is the origin of time. I mean, you can absorb that alpha in the definition of time, right? You can choose your new time such that there is no alpha here. So that's what I meant. So you can redefine your origin of time, and this alpha will go away. But then here I keep it general so that you have some phase here. okay, corresponding to the free case. Anyhow, so that's what it is. And this equation is not homogeneous, okay? This is a non-homogeneous equation. And the most general solution is to this non-homogeneous equation, Q of t would be the homogeneous part, which is a cos omega t plus alpha, okay, plus a particular solution. Right, so I should find out a particular solution to this non-homogeneous equation, and then I'll find the then I will get the full solution. Okay, so that's what we have to do. Okay, now you can, let me draw a vertical line here. Okay, so let me search for a solution, a particular solution of this form. So I say Q prime will be some b cos gamma t plus beta. So that's what I look for, and that I should do, because that's what you have on the right hand side. Okay, and if I substitute this in the equation of motion here in this one, I immediately get b equal to f 1 over omega square minus gamma square. Okay, so the most general solution I have is the following. I should add to the particular solution the solution corresponding to the homogeneous part. Okay, and this is what it is, plus the particular solution. And of course I have forgotten, no, nothing, it's fine. So your, where is b is this, and then you have cos gamma t plus beta. So, and where omega is not equal to gamma, because at omega equal to gamma, this solution blows up. Okay, so now imagine this part is called a transient solution, because if imagine there was friction present. Okay, let's say the pendulum is experiencing some friction, which will be the case in reality. And then let's say also imagine that there is no external force acting on it, and you have a free pendulum. A pendulum which is experiencing some friction. After a while, it will stop, right? Meaning this solution will just go away after some time, if there was friction present, and that's why this is called transient. Okay, so that is the solution for forced oscillations without any friction. Let me write here okay, but this is not valid when your gamma, the frequency of external agency, is same as the natural frequency of the system. It looks like this solution blows up. Okay, so it is not valid here. So we'll next look at this the problem near resonance. So when omega is same, when gamma is same as omega, we say we have resonance. And that's what we want to look at now. Okay, so let me write it down. Okay, so now our equation of motion is the following. Q double dot plus omega square q equals f cos omega t. Okay, I've just put the phase to 0. If you wish, you can bring it back, but I will just put it to 0. And this omega is same as this omega here. Okay, this one and this one are same. Okay, what I can do is I can go to complex variables, and instead of using the real q, I use z. So let me define a new equation. Z double dot plus omega square z equals f e to the I omega t. And if I take a real part of this equation, okay, I will get back this one, okay, where I will define q to be the real part of z. Okay, now as before, because this is a non-homogeneous equation, I should search for a particular solution, and of course I know what the solution to homogeneous part is. So let's go ahead and search for a particular solution. Let's try the solution of this form. So I say the particular solution I will denote by z prime. Okay, so let's say the particular solution z prime is some function of t, which is a of t, times e to the I omega t. Let me try this one out. Okay, you can check that z prime dot is I omega z prime plus a dot e to the I omega t. And if you take a second derivative of this, you are going to get a double dot plus 2I omega a dot minus omega square a. You should check this. I hope I'm not making any mistakes. E to the I omega t. Okay, now you can substitute all the three here. One z prime, z dot prime, and z double dot prime. Put them in the equation of motion here and obtain the following. If you do so, you get the following. You get a to be minus if over 2 omega times t plus k1 e to the minus 2 I omega t plus another constant k2. So k1 and k2 are complex constants. Okay, that's good. Now if I have found my a, I have my z prime, which is the particular solution. Okay, now what I'll do is I'll write down k1 as c1 e to the I alpha 1 and k2 as c2 e to the I alpha 2, where c1, c2, alpha 1 and alpha 2, they are all real numbers. Let me write down alpha 1, alpha 2, c1, c2, they all belong to real numbers. And you get the particular solution to be now z prime equals minus if e to the I omega t over 2 omega, and this entire thing is multiplied by t plus c1 e to the minus I omega t minus alpha 1 plus c2 e to the I omega t plus alpha 2. That's your particular solution. So if I take real part of z prime, then that is what will be the particular solution of this equation, right? Now look at these two parts. These two are, let's take the real part of z prime. real part of z prime is f sine omega t over 2 omega t plus c1 cos omega t minus alpha 1, okay, and c2 cos of omega t plus alpha 2. Now you see these two terms, this one and this one, these are just cos omega t and some phase, and these are the solutions to the homogeneous equation, okay, the homogeneous equation associated with this non-homogeneous equation. So these two you can drop, okay, you can put the constant c1 and c2 to 0, and you can do so because this thing is anyway available in the homogeneous equation. But if you don't want, it doesn't matter, you can keep them, and when you add everything, you can combine this and the one with the homogeneous again to one function, which will be cos omega t plus some phase times some constant amplitude, okay. So either way, whichever way you prefer, you will have only this piece and the homogeneous part. So I'll put the constant c1 and c2 to 0. So my particular solution is f sine omega t over 2 omega times t. Okay, and as I said, I can write down my solution q of t to be some constant a cos of omega t plus alpha, okay, plus the particular solution okay. Now you see I don't have any singularity at omega, I mean there's nothing singular going because omega is equal to gamma. There's no singularity here, okay, as we had in this case, if you see here. Okay, that's good. So this is the right way of doing it. Now if you look at the solution carefully and pay attention to this term, you see it is, of course there is a harmonic variation sin omega t here, but you also have a t proportionality here, which means that your solution, your displacements q of t, they are growing linearly with time. So this grows linearly with time, right? So at some point of time the displacements will be large because as time grows the displacements grow linearly, okay, and your approximation that you are close to the equilibrium will no longer hold true, and all the other terms that we have dropped in linearizing the equations of motion, okay, they would play a role, and this solution will not be valid. But if you are looking at only small values of t, then this is fine, then this is the solution, okay. So for large t, the approximation of small oscillations breaks down. Okay, next we should look at damped oscillations, okay, and then we will have both damped as well as forced, or everything present together, and we'll look at the solution in that case. And eventually we would like to see what we can say when we have not just a system of 1 degree of freedom, but as we have been discussing before, what happens if I have a system of more than 1 degrees of freedom. Can I do again 1 what I was doing and bring in normal coordinates. Okay, so that will be the our next task.